Good morning. My name is Lauren Dow. I'm the Communications Coordinator for the Office of Materials and Road Research and the National Road Research Alliance. Thank you for joining us for today's Research Pays Off, hosted by the NRRA. We're glad you joined us. This session is being recorded, so if you do not wish for your image to appear on the screen and be recorded, then please keep your video off. We're using Teams today, and to minimize potential bandwidth issues, we would ask that you keep yourselves muted and your video off through the presentation. We will be hearing from both of our presenters this morning, leaving time at the end for questions and discussion. So during the presentation, you're welcome to use the chat box to ask any questions you might have, and then we can address those at the end. I did want to make a quick reminder about the Minnesota Transportation Conference and Expo that's happening in March 1st and 2nd here in St. Paul. The National Road Research Alliance will have a booth at that event, and there's lots of opportunity for vendors to have booths as well, and lots of other things going on. I'll be sending out a flyer later today with a lot more details and links to the website to register or to get a booth yourself. I also sent out the next 3 months of Research Pays Off invitations, so hopefully you all received those and can get those on your calendar blocked off. Today we're hearing from the Flexible team as part of our makeup for the meeting that we did not have this year for the NRRA. So this is the project that was voted to be heard from. And so we've got Eshan and Katie Haslett, who are here to present on behalf of the team. And I will give it over to Eshan.
Thank you very much, Lauren, and I'll in interest of bandwidth, I'll keep my camera turned off, but maybe during question answer, I can turn it on as needed. I'll just very quickly do a self-introduction. So I'm Eshan Dave. I'm Associate Professor at the University of New Hampshire. And this project that you'll be hearing about today is actually one of the recently completed projects. The final report was published earlier this year, and the project has been completed. This was one of the phase 1 NRRA projects from the Flexible team, and the project I was project principal investigator along with my colleague Professor Josiah as co-PI, but real force behind this project was our star Ph.D. student at the time, Katie Haslett, now Dr. Katie Haslett. Katie's finished her Ph.D. earlier this year and is now working for the Heritage Research Group. So as you can see in the title, this project really focused on trying to come up with a practical tool or tools that can inform material specifiers, pavement designers in selecting appropriate asphalt mixtures for use in asphalt overlays that are put as a rehabilitation treatment to Portland cement concrete pavements. And hopefully everyone can see my screen, but if you have any issues or anything like that, please feel free to stop me. The idea here is for me to give some general introduction in the first part of this presentation, and then I'll hand it over to Katie, who will really walk you through the most important outcome of this project, which is the decision tool that users can use in order to do selection of materials as well as pavement design. I am hearing some kind of noise in background, so I don't know if someone else has their microphone unmuted, but if you are able to mute it, I would appreciate it. So just very quickly introducing reflective cracking as a distress itself. I don't think this group really needs much of an introduction on what reflective cracking is. Pretty much everyone who's involved with NRRA is very aware of this very detrimental distress. It's a distress that usually controls the life of your overlays. and its formation is really driven by those stress concentrations that happen within your asphalt overlay right on top of your underlying Portland cement concrete joints, or cracks in your underlying pavement if overlays on asphalt pavement. And because of that reflected pattern of that underlying joints or cracks is translated into the overlay. That's why we call this type of cracking as reflective cracking. A big challenge is not the cracking itself, but really the loss of serviceability that results from this cracking. Once you have cracks forming, it allows water to really infiltrate into these cracks, start to have the crack degradation and deterioration, resulting in severe bumpiness or increased roughnesses of your roadway, and obviously loss of structural integrity. And as I mentioned earlier, there's really the mechanism that controls typically the life of your asphalt overlays, and asphalt overlays are most commonly used rehabilitation treatments. So it's important for us to study this this challenging distress, and even more important to come up with practical solutions that can allow us to delay the formation of reflective cracking on our overlays. So in terms of the overview of the project itself, and in this one long sentence, it really describes all the attributes or facets behind this project. The project was really designed to come up with a decision tool that can be easily put into practice for selecting suitable asphalt mixtures that have potential to delay formation of reflective cracks, and also couple it together with your overlay thickness design. Now, keep in mind that current procedure for most agencies for overlay thicknesses is really policy driven and is not really mechanistic. However, as an outcome of this project, and I think in general there is more awareness about this anyways, we are seeing that we really need to start thinking about overlays and designing overlays the same way we design our conventional asphalt pavements, where we have to put some thought into the thickness design of overlays. While some tools exist, I think that's very much, or at least before this project was very at regressed airvoid type of mixes, where you have a little bit extra asphalt binder into these mixes by lowering the air void, by adding extra binder, or methods that initially were developed in Indiana and now getting more and more widely accepted, such as Super Pave 5, where you are using a different way of packaging your aggregates in order to design and construct your asphalt mixtures at same air void level. Once again, trying to really improve the durability of these mixtures and cracking resistance of these mixtures. So this project also looked into that aspect, as you'll see in coming slides. So just to give you an overview of project, and I won't go through task by task, but just in a nice 10,000 foot view type of approach. So the project really tried to combine two things. As part of this project, since this is an NRRA project, and it consisted of multiple min road test sections that were constructed, we are really looking at taking the field performance as well as the lab characterization of these mixes, put them into mechanistic models in order to expand the performance data set, because we cannot construct 100 different test sections. So we are limited by how many test sections we construct. However, using that information, if we are able to calibrate and validate our mechanistic models, that allows us to then use parametric evaluations to significantly expand our data sets. Using the mechanistic analysis as well as the field performance data, the next task was to come up with models that can actually predict performance curves for these overlays, that can predict the rate of cracking in these overlays as function of the structure, the underlying pavement condition, the traffic level, the material choices, and other variables. Once you have that done, the next aspect included to support the decision tree tool to really look at doing life cycle assessment as well as life cycle cost analysis. And that's important because we cannot really make our decisions, especially in a rehabilitation type of scenario, solely on initial cost. We should be looking at life cycle cost. And obviously, we should be paying attention to what's the impact of our decisions on our planet, and hence life cycle assessment. There are really two different attributes that were looked at or that were part of the project itself. So obviously one side is selecting overlays and materials for them and their thicknesses, but at the same time there's always an option to also look at, can we first repair the existing concrete pavement, or at least do a partial rehabilitation on it to improve its current condition before overlay is placed. So for example, things like load transfer restoration. Can we do a load transfer restoration? And if we do that, then what's the impact on how much of asphalt thickness I need and what kind of materials I need? So we looked at some treatments there. One of the other treatments, as you'll see on later slide, was also a grout filling underneath the slabs, although that did not pan out very well in this particular experiment, as you'll see in the results. And so obviously the final outcome, as I've already alluded multiple times, is a decision tree tool. And Katie in her part of presentation will be going through the tool and its development and functionality in quite in depth. So what are different materials and field sections that we evaluated? There were 12 different main road cells that were constructed. All of these were constructed on the old I-94 bypass. So there's really old concrete pavement with relatively low load transfer. I took the slide out that showed load transfer efficiencies, but the load transfer efficiencies range from as low as mid-30s, so pretty much non-existent, and that was primarily in driving lanes and passing lanes. Higher values, but not necessarily stellar, but typically mid-70s in the passing lanes. In terms of the sections, the really things that varied are shown on this slide. So you can also see the control section, which was 9.5-inch concrete with inch and quarter dowels, 27 feet joint spacing. But the overlay variations included thicknesses, mix types in terms of gradations and how mixes were put together. Density, that's really tied to that regressed air void versus super pave 5 versus traditional super pave design of 4% air voids. And also several sections had interlayer type of treatments where we used a 4.75 millimeter highly polymer modified mix, somewhat similar to the 475 millimeter mix that Illinois DOT has, or the CAM mix that Texas DOT uses. Also, from tack coat application perspective, some sections were paved with spray paver with different rates of tack coat to look at whether that had an effect on reflective cracking performances or not. So overall, if we just look at our palette of different sections here, all 12 of them shown, and I know it's overwhelming to have all of this information on one slide. So I'll try to make it a little bit simple, or Katie did at least in preparing the slides, and that is if you look at just some color coding, you can see all of these red sections, all 5 of them are actually 4 inches of asphalt overlay. So they all have same total overlay thickness. All of them have a common 2.25 inch 19 millimeter mixture as your first course. And then the top course really varied, and cells 988, 89, 990, and 991. The only difference between them is really how the mix is designed. So they all use the same aggregate sources, same binder grades. First 3 are all 12.5 millimeter mixes. 88 designed at 4%. 89 designed with super pave 5 type of concept, and 990 designed with regressed air void with a little bit extra binder in it. The next 2 cells, 992 and 993, are slightly thinner, so they are 2.5 inch, what would typically count as a typical thin overlay treatment that many states use. But both of those also had an interlayer type of mixture, when 992 had a 1 inch highly polymer modified asphalt mixture versus 993 went with a more of a permeable stress absorbing coarse type of approach, so it uses the PASB or PAS-RC type of mixture that MnDOT oftentimes uses actually also underneath their concrete pavement. So it's a very open mixture, and the idea was with that openness, you might have higher strain tolerance. 84, 85, 86, and 994, they were all 1.5 inch, mainly looking at the effect of the tech coat application and use of spray paver versus conventional paving. With 994, the main difference is here the slabs were void grouted as opposed to the companion section, for example, 984, which is identical to 94, where slabs were not grouted. So we wanted to see the effect of that grouting. And then 995 was your make it or break it section of just a 3/4 inch ultra thin bonded wear course, and that's it. So really thin overlay, just trying to see what kind of survivability we might get from doing such a thin overlay. From lab performance testing perspective, the study was not really focused on trying to look at which lab test works or which does not work. That's already part of NCAT Min Road Cracking Group experiment, and there's multiple efforts on that side. So this study did not really focus on that aspect, but nonetheless, this study did provide an opportunity for us to at least get a glimpse into which test might correlate to field performance or not. And as this is NRRA, various agencies participated and conducted a lot of different type of tests. I'm only showing you the tests that were mostly cracking related, but there were also Hamburg wheel tracking tests done. Missouri DOT did extensive amount of allotment testing on these mixes. Michigan Tech University actually did some mist conditioning on these mixes. So there are a lot of different type of tests conducted. And in report, we have quite extensive amount of statistical analysis to compare how these tests relate to mix performance or relate to each other, as well as mix composition, as well as also to the field performances. But bottom line, what we found is at least from the cracking perspective, there's somewhat agreement between which mixes were best performing versus poor performing. Almost all tests indicated the 475 mix with a 58E minus 34 quite highly modified binder to be the best test or best mix. Whether it's a low temperature testing such as dish shape compact tension, or intermediate temperature testing, which is done with flexibility index test or Illinois flexibility index. Now for each test, we also tried to use every possible performance index that people have proposed. With most of these fracture tests, there are some kind of post-peak shape based indices. So we also included that in the evaluation. We did do some basic modulus measurement because that was necessary for mechanistic modeling. It was nice to see that you could see as expected trends there as well. So in general, as our air void increased, going from 3 to 4 to 5, your stiffness was decreasing, which is typically what one would expect with the effect of air void on your stiffnesses. And then lastly, we also, as you saw on previous slide, the testing also included some of the simulative type of tests, such as Texas overlay tester. And there also we still had good agreement with some of the monotonic tests, such as flexibility index, where once again that 475 mix was shown to be the best performer, and this particular half-inch mix to be shown as a worst performer. Now, field performance information, and this is really important because this is the gold standard, right? We can argue about mechanistic models. We can argue about whether a specific test is able to distinguish a mix or not, but you cannot argue about what happens actually in the field because there's a control experiment. All of these sections are seeing same climate. They're all seeing same traffic. Every single truck that goes through one section goes through all the other sections because they are all located on same stretch of highway. So if we look at the outcome, and again, I apologize for a busy plot here. So let's get you oriented a little bit here. What we are looking on this plot on the vertical axis is the amount of reflective cracking, and the amount of reflective cracking is really defined because we knew where underlying joints were in the existing concrete pavement. When you have 100% reflective cracking, means that every single joint that's in underlying pavement has reflected in form of a crack at that location within the overlay. So 50% means half of those have reflected, and so on. Now, horizontally, what you are seeing are different sections, and all 12 of them are shown here. If you recall, 988 to 991, and I'll just bring your attention to those because they also have consistent structure. All of those are 4 inches. They all have same first course. The second course is where it varied, where you are looking at the type of mixes that are used with regular super pave mix, 3% or regressed air void mix, actually super pave 5 and then regressed air void mix, but those are the middle two. And then the last one I believe was that 9.5 millimeter, the slightly finer gradation mix. So if we look at these results, the green dots are after one winter, really after 8 months, and then the last set of points are after about 3 years in service. So you can see that apart from those really thick sections, for most of the other sections, they did sort of reach a terminal reflective cracking value. Maybe not in terms of serviceability, but at least every single joint did reflect through completely into the overlay by the time the study duration was over. The thicker sections performed well, and specifically those regressed air void and super pave 5 mixes did really well compared to many of the other mixes. And I say that not just because after 3 years they stayed below 50%, but even if you look down here where some of these sections after about a year in service, they had already climbed up to above 50%. Many of these sections had no cracking after almost after 1 year, and a moderate level of cracking after 2 years, and it stayed there. It did not continue to climb up. Other than that, I'd also like to point out to 2 specific sections, the 987, which also had 4-inch thickness, it did quite well, and 992, which was the much thinner compared to these other ones. These are all 4 inches in thickness. These is 992 is only 2.5 inches in thickness, where it used that 1-inch interlayer mixture, which had very high strain tolerance, and you can see the improvement in performance from that. Now we can also use that same information and try to process it a little bit further and give some credit to the thicknesses of overlays. So that's what we are trying to do here. So what you are seeing in the previous slide is really the raw data of actual reflective cracking amounts. Here it's more of a processed information, and what we have done is we've looked at into a field performance measure called RC total. And the idea behind this measure is that it allows you to take your amount of reflective cracking and puts a time value to it, so sort of rate value to it. So even if after 30 months or 36 months, you may have 2 sections that have 60% cracking, if the first section cracked early, it has a poorer performance because it was not able to survive for as longer of a duration as the second section did. So here we have bars that show from different times, but really we can just look at the last set of bars because that's the most recent data. And once again, the story is more or less same as what you saw on previous slide. 990 was our best performer. Keeping in mind that here we also consider the thickness. So yeah, you are putting 4 inches of thickness, but we are thickness normalizing these sections. So now we have taken the structural effect out of these sections. So you can really start to see that overlay thickness does matter together with the mix. So it's really a combination of both and not just one, because oftentimes people say, oh, it's just if you put 2 inches of thickness, you get X number of years. That's not true. It's 2 inches of thickness and which mix that together is the important part. The only other thing I'd like to point out is 9954 did not perform well. It actually had the worst performance, and that was the section that was constructed with the grout sealing of the slab. So 984, 994 identical. 994 actually had slightly better LTE, and yet it performed really bad. So in this particular experiment, that grout based method for sealing the voids under slab actually resulted in poorer performance. So just to complete my story about how you have to look at structure and a mechanical property, here's one parameter that I'm showing. And all these parameters really doing is combining your fracture resistance of overlay in terms of its fracture energy multiplied by its thickness. And if we compare that total fracture resistance together with RC total, not thickness normalized, because we are accounting for thickness in vertical axis. So horizontal axis does not have to have it, otherwise you are not really comparing in a fair way. You can see that we actually saw somewhat of a reasonable trend where mixes that had either high fracture energy or overlays that had high thickness perform well, and overlays that were either thinner or even moderate thickness but poorer fracture energies did not perform well. So bottom line, we have to combine structure and material to really get good performance. Mechanistic modeling, I already mentioned why we did mechanistic modeling. We did it to expand our data set that can be used to develop decision tree tool. Since we only had 12 sections, we wanted to have larger amount of data set to do the tool development and to better understand what variables are impacting reflective cracking and how. So we did it primarily with Ashtaware Pavement ME, as well as a lot of in-house work with finite element software with cohesive zone model. I won't go into detail on the mechanics behind it, but just summarizing it, we actually saw quite good agreement between field performance and Pavement ME. With finite element modeling work, when we use the historic climatic data, we saw maybe a fair agreement, but what was most eye-opening was when we actually used thermal data from instrumentation at Min Road. We saw very, very high potential for thermal reflective cracking or thermally driven reflective cracking on the overlays at Min Road, which is also matches well with field observations. After each winter, we saw quite significant jump in the amount of cracking. And that really goes to show that in cold climate, you can get quite a bit of reflective cracking even without traffic, just because of the thermal action. And there's just one example of parametric evaluation that we did using the data from using mechanistic models. Since I'm out of time, I won't spend time talking about it. So with that, I will hand it over to Katie for her to talk with us about the decision tree tool.
Great. Thanks, Dr. Dongwei, for kicking us off. So in the next several slides, I'm going to cover more of the background and the development of the decision tree tool, which was kind of ultimately the major project deliverable from this research study. So there are three main components of this tool that the user gets to interact with. There's an introduction, an input, and an output tab. Within that introduction tab, it contains really a statement of the purpose of the tool. It provides users with instructions as well as a glossary of terms and assumptions and system boundaries. The next tab is where the user is prompted to enter information on things such as project details, analysis options, what that existing PCC condition is, as well as underlying pavement structure, an estimate of the expected traffic level, and what their target performance criteria is, so how many joints reflected over that analysis period, and then lastly, some unit cost inputs. The final tab that the user gets to interact with is the output tab, which provides predicted pavement performance curves, and as well as a life cycle cost estimate and a summary of what the traffic level is over that analysis period. So just to dive in a little bit more and provide a little bit more context on some of these inputs and outputs that are driving the decision tree tool. The tool itself is Excel based, and that was intentional in order to try to keep the tool accessible and relatively easy to implement by agencies without use or need to purchase, say, additional software. Some of the basic inputs considered in the overlay decision framework are the initial load transfer efficiency, or LTE, and that's used to characterize what that existing PCC condition is. And the decision to use that really as the primary input for the condition of that concrete layer was based on findings from literature that really support it being a significant input parameter to consider on, and especially its influence on reflective cracking. For material choice, users have the option to select from a pre-populated material choice or to enter a user-defined mixture type. So if a user wants to put in their own agency's mixture, they will be prompted to enter as well some lab measured properties of that mixture. In terms of thickness, the overlays can range from as thin as 3/4 of an inch to as thick as 7 inches in total thickness. Traffic is estimated using an average daily traffic in the design lane, as well as whatever the percentage of trucks is in that design lane. For desired performance, it's specified in terms of what percentage of joints reflected over the analysis period is desired or targeted. So for example, if you wanted to try to mitigate or keep below, say 90% of your joints reflected. And then lastly, for cost, there are really kind of two components of the cost inputs. There is a unit cost for the material, as well as an all-inclusive construction cost, which includes the cost for the preparation, the placement, and striping, and so on. And then I think if you click again, there we go. The outputs for the tool, as I previously had mentioned, are first the pavement performance curves, and those are given in terms of truck traffic as well as with time. And then a life cycle cost estimate. And right now in the current version of the tool, that life cycle cost estimate is really only based on an agency's cost impact and excludes user cost impacts. The cost is presented in two different manners: a net present value, where all future costs are discounted back to a present value, while also taking into account any salvage value at the end of that analysis period, as well as an equivalent annual cost, which essentially represents what an agency's expected annual cost is of maintaining that overlay during that specified analysis period. So I'd like to just spend a little bit of time to go into detail on how these predicted performance curves are generated. And they were generated using a combination of the lab, field, and the predictive model results that Dr. Dawe had kind of gone through at the beginning of this presentation. And so the approach really begins by plotting reflective cracking versus the 6 different survey dates for our driving and our passing lanes separately. So if you follow along on the right side of the screen here, just as an example here, we're showing the reflective cracking with months in service. The next step is to fit that data using a common mathematical model that's able to follow kind of an S-shaped decaying pattern. And in this research study, we selected the Boltzmann sigmoidal fit-in function to fit that data by trying to minimize the sum of squared residuals. And I'll note that there are kind of 2 key fitting coefficients to this equation: a half value and a slope, highlighted in red in that equation. And then lastly, to be able to try to account for variability in our predicted reflective cracking amount, we also constructed a 95% confidence interval around our reflective cracking amount, and that's shown on the plot on the right with those red and blue dashed lines. Now, the process that I've really kind of explained so far has gotten us one piece of the puzzle. And if you recall from the beginning of the presentation today, Dr. Dawe had mentioned that reflective cracking is driven kind of by 2 loading mechanisms. You have your thermal and environmental piece, and directly taken into account by time, as well as a traffic piece. And a valuable lesson that was kind of learned, or an outcome from this study, was really the challenge associated with trying to decouple these 2 factors, especially in colder climate regions such as Minnesota. And it's important to be able to consider both of these loading mechanisms in the formation of reflective cracks. So for that reason, we followed the same process, and we fit our reflective cracking versus the total number of trucks at each one of our survey dates, and then determined what those Boltzmann fitting coefficients were, the slope and the half value. We then looked to try to combine these 2 plots into one single plot. And that was done by changing the x-axis to be defined as truck months. And you may be wondering, how do you get to truck months? Well, we took whatever the number was of months at a given survey date, and we added the cumulative number of trucks multiplied by a scaling or a conversion factor. And that scaling factor was different for our drive-in and our pass-in lanes. And that was done to be able to take into account differences in truck traffic volume that were experienced between the 2 lanes. Now, this process, we repeated it for all of our min-road test sections for our drive-in and our pass-in lanes separately, which gave us a total of 24 kind of unique Boltzmann fit-in functions. The next step in this kind of framework to develop our performance curves was to split this data into two groups, and they were split based off of what their pre-overlay load transfer efficiency was, or LTE. So if a test section had an LTE that was greater than 50%, we consider it to be in a moderate LTE group, and if a test section had an LTE lower than 50%, it was in the low LTE group. We then calculated something called a total performance index, and we did that for various different cracking tests. So we started off looking at dish-shaped compact tension, the semicircular bend, and the overlay tester, and looking at different performance indices from those different tests. Now that total performance index is simply whatever that measured lab property is multiplied by the contributing layer thickness. So just as an example, on the right side of the screen, I'm showing a plot with the slope Boltzmann fitting coefficient on the y-axis, and on the x-axis, DCT total fracture energy contribution. So let's say you had a 2-inch overlay that was made up of a single material with a fracture energy of 500, then your total fracture energy contribution would be 1,000. And here you can see too that we fit these two LTE groups separately with the red and the blue lines here. And by establishing this relationship, we are now able to, it provides a link for us to be able to predict our Boltzmann fitting coefficients, so the slope or the half value, which are needed to be able to construct our reflective cracking performance curves for any, say, overlay design that's different than our min-road test section. So if we had a different material or maybe a slightly different thickness, we're able to predict what those fitting coefficients are. And just as a note or an aside, but while fracture energy was used as the lab measured property in the current version of the tool, as part of the report and as part of this project, we also looked at other performance indexes that could be used for this relationship to predict those Boltzmann fitting coefficients. And as in the report, we outline kind of how an agency could take this framework and then also look at, say, if you were interested from semicircular bend, using flexibility index to come up with that relationship, that you could manually edit the tool to account for that. So on this slide is just showing a visual or a screenshot to help kind of pull things together on what the output tab looks like from this decision tree tool. So if you'll follow me from the top kind of left, it provides a summary of what that overlay design is. In this case, I was looking at a 4-inch total thickness overlay made up of 2 different lifts. And on the bottom are those predicted performance curves given both in terms of total number of trucks as well as months in service. And then in the upper right corner is where that life cycle cost analysis estimate is given, again, both from a net present value point of view as well as an equivalent annual cost, and that's based on just an agency's impact, so no user cost is included in that. And then underneath is just a truck traffic summary of what the inputs were and what that total number of trucks were over the analysis period. So just to summarize today's presentation and some of our conclusions and recommendations, we know that reflective cracking continues kind of to be a prominent distress in rehabilitated concrete pavements. And so this research study looked to evaluate mechanistic models, laboratory and field performance of our min-road sections, ultimately to develop a simple decision tree tool that practitioners could use to be able to select both asphalt mixtures and overlay designs in an attempt to try to lower or mitigate reflective cracking. Some of our kind of key recommendations from this work were that in general, we saw our thicker pavement sections are better performing over the long term. And when you look at performance indices such as RC total that are able to take into account structure as well as kind of cumulative performance, so whether a test section cracks early versus later in its service life, it helps to kind of more fairly compare some of our sections. And so when we look at an ultra-thin bonding wearing course that was used in 995, it shows promising results, as well as if you were to use that overlay in combination with another mixture to provide kind of a little bit further structure. From a material standpoint, we saw that our regressed air void and our 5% air void design mixtures used in those surface lifts were the top performers in the field, as well as from lab testing. And then as Dr. Dawe had mentioned a few times throughout the presentation, we didn't see any significant improvement in field performance by performing that slab stabilization using the polyurethane grout filling. But I will say that with a caveat that this conclusion is really based on kind of one comparison, cell 984 to 994, where they were identical in structure, but 994 had that void grouting prior to overlay construction. So then lastly, just to kind of wrap things up and to think about kind of what are the next steps and where to from here. There is a current phase 2 for the reflective cracking study. There's an RFP ongoing for the Min Road Reflective Cracking Challenge, or MERCI project. And in this project, it's being proposed to look at HMA over HMA overlays this time, as well as look at adding a life cycle assessment piece to the decision tree tool. So to build off the life cycle costs and also look at the environmental impacts of the different overlay design alternatives. And in conjunction with the additive group experiments, some of those surface mixtures will be used in the test sections, as well as some of the top performers from this phase 1 reflective cracking study. And so looking at including the regressed air void as well as that 5% air void design mixture. And with that, I think we'll turn it over for questions and comments.
Thank you so much to you both. We do have a question in the chat box, and this is from How, and I believe it was during Eshan's portion. How reasonable is it to assume linear progression RC total percentage per month?
Good question, How. I don't think we need to make that assumption that RC total progression with time has to be linear. I mean, as you saw in Katie's presentation, okay, there we were just talking about the reflective cracking amount itself. We did not make that assumption. We really just started with the data that we had, or as we had. So it's really whatever the actual sections did in field is really what we used. It's not to say that some sections did have linear progression for part of the evolution, but really the reason you see those straight lines between the dots is we did not want to force a fit through it. So those each measurement is just each survey date. So hopefully that answers your question.
Thanks, and I'd like to invite you, if you have questions or comments, you can go ahead and unmute yourself. I do see a hand raised here.
Yeah.
Whoever that is.
I think Hiab.
Hiab, yes.
Good morning, it's Hiab. First of all, I would like to congratulate both of you and your team. This was an excellent work and excellent presentation. I have one comment and one quick question. The comment is based on your slide 3 picture.
Yeah. Yeah. Give me just a second. I'll pull that up. Go ahead.
So, looking at this picture, it could be anecdotal, but it seems like that the cracking starts from the top and propagated down.
Sorry, but I will put a disclaimer. This picture is not from this project. It is picture that I was involved with the project where we took it. But just so that you know, this one is not from this particular project.
I see. Yeah. Okay, so my comment was going to be then it makes sense that you find also by looking at the thermal data, this is a fraction energy.
Exactly.
So yeah. In fact, it makes sense from all the testing that you looked at that the fracture energy work. So that was my comment. Yeah. The question is.
Thank you very much. And I just to not to respond, but I just agree with your comment completely. Yeah.
And my question was that related to that, since you have 2 lifts of overlay, some of them 19 millimeter and 12 millimeter and 4 millimeters, and the fracture energy results or all the test results that you showed for each test section, were they performed on which one of these lifts?
No, that's a very good question. We actually take cumulation effect of those lifts. So for example, if you have 2 inches of 19 millimeter mix, and then 1 inch of 9.5 millimeter mix, really the fracture energy is cumulation of all of those together. That's why we combine the structure contribution with the material contribution. So it's 2 inches times whatever's the property, and it doesn't have to be fracture energy. It could be flexibility index, for example, but it's 2 inches of flexibility index of value A plus 1 inch of flexibility index value of B, and that becomes our performance measure that really is used in the decision tool.
I see. Thank you very much, Max. Thank you.
Good question. Thanks, Ian.
Any other questions or comments out there?
While people are thinking, I would like to say I should have mentioned it in the presentation, but Shongtao Dai from Minnesota DOT was the technical liaison on this project, and we also had a very active and very helpful technical advisory panel that they really helped us tremendously in reviewing our work and also making very good suggestions along the way. I mean, they had quite significant input in the decision tool that we ended up with at the end. So that really appreciate all the input and all the effort of everyone involved.
Yeah, if I could just echo that, just a thank you to also some of the MnROAD staff too, helping with collection of that data and throughout the project and stuff, and the many data requests. So greatly appreciated. It was great working with all of you.
And congratulations, Katie, for your new gig.
Thank you very much, Ian.
We do have a few more minutes here. So I'm open to taking any more questions. Otherwise, we can just end a little bit early today. So once again, thank you, Eshan and Katie, for your time and efforts put into this project, and also to Joe Sias as well.
Yeah.
So
thank you very much, Lauren, for hosting us, and thank you, NRRA, for letting us make this presentation today.
Yes, and I appreciate your shout out to the TAP, and just a reminder that we really don't usually have any limits to how many people can be part of TAPs, where it seems like we're always kind of looking for more people to provide their input into, our projects and things. It looks like I do see another question here.
Yeah, a very good question. Thank you for bringing that up. Actually, that's something that we are trying to work anyways on, is to get the tool posted on NRRA. I think we'll we'll work with Lauren to get that posted on the project page, because I think the final report is posted, but the actual tool is not there. So we'll try to get that posted pretty soon here.
Yes, sounds good. We can work on that. Great question. Well, this recording will be up on YouTube if you want to go back and look at something or pass it on to any colleagues or anything. And I think we will sign off for today. And thanks for joining us. We'll see you next month in December.
Thank you.
Thank you very much. Take care. Bye-bye.
Thank you.